Hi everyone, thanks for joining us today. I'm Stephanie, and today I'll be taking you on a deep dive of the Ray memory management system. Before we start, let me tell you a little bit about myself. I'm a software engineer at Anyscale and also a PhD student in distributed systems at UC Berkeley. The majority of my work at both Anyscale and Berkeley has been on the open source Ray core. You can think of that as the backend for all of the Ray application libraries like rllib, tune, and more. The Ray core team spends a lot of time making sure that the backend can provide reliability and performance for the huge variety of applications that other developers build on top. So today I'll be giving you an overview of some of that work. Since I'll be focusing specifically on the memory management system, we'll be going in depth on a bunch of topics related to Ray objects, such as object storage, the ray.get call, and memory deallocation. Before we get into the specifics, let's take a high-level view of the architecture. One important thing to understand is that under the hood, the system treats small and large objects differently. That's because these objects have different properties in terms of memory usage and how long it takes to get the value. So Ray will attempt to optimize performance depending on the object size, and meanwhile, the user can ignore all of these details and reason about program logic at the level of object refs. We'll see how this translates to the physical design next. But first, let's take a look at the overall Ray architecture to see how the memory management system fits in. One of the head nodes in a Ray cluster is designated as the head node, and that's because it hosts the global control store, which manages system metadata that may be accessed by all of the nodes in a cluster, such as a directory for locating objects. We also have the driver, which is the root Python process of an application, and workers, which are Python processes that can execute tasks. On every node, we also have one process known as the raylet, and the raylet has a scheduler thread that manages resources and an object store thread that manages memory. A Ray cluster can also have many other worker nodes, and these nodes all look like the head node, except that they don't have the global control store. So one thing to note is that the global control store could actually live on any of these nodes, but currently it resides only on the head node. The memory management system is actually a subset of the overall Ray architecture. For this talk, we'll focus on just these components. First, there's the object metadata, and for both small and large objects, the metadata is stored at the process that created the initial object ref, and we call that process the owner. For example, if a worker calls a remote function foo and that returns an object ref to x, then that worker will also own the metadata for the object x. The owner process is important because, as we'll see soon, it's involved in most of the system operations related to that object. Next, we'll look at the architecture differences for small versus large objects. Small objects are quick to copy, and you can store a lot of them at a single process. That's why we store these directly at the owner. If another worker needs the object value, we can simply copy the object to that worker. That makes reads really fast, and it's also easy to understand how failures work. If the owner fails, then the object will fail too. But there are some downsides in extreme cases where an object is referenced by many workers. For example, passing a small object ref as an argument to many tasks can be inefficient because each task would require one copy. Large objects are more expensive to copy, so we have to navigate a different trade-off depending on the object size. Instead of storing the object value directly at the object's owner, we store the object in the distributed object store. So while one Python process might have the object ref, the actual value may be stored at a completely different process, maybe even on a different node. The main benefit here is that the object store on each node can be implemented with shared memory, so we can leverage that to reduce the number of copies. On the other hand, it can take longer to read an object since it's stored at a separate process, and the failure model is more complicated because now we have a distributed system. Now we'll start to look at how that architecture actually gets used. To do that, we'll discuss each of the different steps that are involved in an object's lifetime. To illustrate these different steps, we'll use the simple Ray program as a running example. Here we have two remote functions, one that returns an array of random numbers, and another that takes an array as the argument and computes the mean. We'll invoke two tasks and show the resulting task graph on the right. First, we'll invoke a task to compute a random array, and the system will treat this as a large object. This call returns an object ref to the caller, or a future that will eventually get populated by Ray with the task's return value. We can pass this future to another task to indicate a data dependency, and the second task will compute and return the mean, and this time the system will treat this as a small object, since it's just an integer. So that program looked simple enough, but under the hood, there's actually a series of steps that the system has to take during the object's lifetime. First, the application creates the initial object ref, and this happens whenever a task is invoked, such as with the call to random.remote. From here, the system will ensure that the task eventually gets executed and that the object value can eventually be read. Next, the application can create other references to the object value even before the object value has been computed. For example, our program did this when it passed the array object ref as an argument to the mean task. Once the task actually executes, we can allocate memory for the returned object. And now that the value is available, other reference holders can get or resolve the value of the object. So for example, the downstream task that we submitted earlier could resolve its reference to array and start execution. While this is happening, it's also possible for more references to get created. For example, we might want to pass the object ref to other tasks. And finally, at some point, all of the references to the object should get deleted. Ray implements a distributed reference counting protocol to figure out when this happens. For example, the system will wait until any tasks that depend on the object have finished execution before it decides to finally deallocate the object. As a user, this is convenient because it means that you don't need to worry about manually freeing memory. You can just delete an object ref once you're finished with it. Now we'll look at each of those steps in detail, and the first step was the creation of the initial object ref. So in our program example, this happened when we submitted the two tasks. Let's see how Ray executes this on a cluster. For now, we can just focus on the object store components of the architecture. Eventually, the tasks will get executed here, but for now, we'll just focus on the driver. And that's because the initial creation of the object ref is a completely local operation. Like I mentioned before, the object metadata is stored at the owner, and there are other types of metadata that get stored here, like the ref counts, but to keep things simple, we'll just show the object's value for now. As the driver runs the application code, it will invoke the first task, which creates an object ref, and at this point, we'll add a metadata row for that object to the driver's local memory. Since object refs are also futures, the value is going to be unknown initially. That also lets us invoke the next task immediately without waiting for the first task to finish. You can see here that we're also creating a reference to the array object by passing the object ref as an argument to the new task. Similar to before, this remote call will also return an object ref, and although we don't store this one in the Python code, the driver will still add a metadata row for this new object. Next, let's talk about the creation of the object value. We'll start with allocation for the large object, which was returned by the random task. To start, we have to schedule the random task on a worker. Let's suppose that we have another node with a worker on it, and so we can send the task to that worker for execution. Once the worker finishes the task, it stores the return value in its local object store. Next, the worker responds to the task's caller, saying that the array is now in the distributed object store. The driver updates its local metadata to record the fact that the actual object value is stored in the remote object store. And this way, you can sort of think of the driver's local value as a pointer into the distributed object store. Another important thing about this design is that the first copy of the object is known as the primary copy. That's because Ray will guarantee that it stays pinned until the object is safe to deallocate. Now that the object value has been created, we can resolve an object ref and get the value. To show how large objects get resolved, let's look at the mean task and see how it resolves its reference to the array object. To resolve large objects, we'll need a way to figure out where objects are located. This is where the object directory comes in. This directory stores the current locations of all large objects, and it lives on the head node as a part of the global control store. Each time an object is created in an object store node, the node will asynchronously add itself as a location in the object directory. Since the object directory is globally accessible, we can use this on other nodes to figure out where to find an object. Let's say the mean task gets scheduled to run on a third node. Now that we have a value for the array argument, we can also send the mean task to be executed. We'll send the task over like before, but this time we'll also attach a message saying that the array can be found in the distributed object store, and that will let the worker on node 3 know where to find the object. From here on, the caller is no longer involved in the object transfer. This is to reduce the bandwidth that's needed at the caller. So even though the caller can specify data dependencies through object refs, it doesn't have to ever see the object data. Instead, each node that needs the object will copy it directly from another node. For example, node 3 can now ask the object directory for locations of the array. The object directory responds saying that the object is on node 2, and now node 3 can ask node 2 for a copy of the object. Node 2 sends a copy over to node 3, and now this worker can begin executing the task. As you saw, the process for large objects can get pretty complicated because we have to use a distributed protocol. Small objects are relatively easy to handle since they're not as expensive to store and copy. To show this, let's see what happens when the mean task returns its result. Since the result here is just an integer, it should be pretty small. For small objects, we never need to communicate with the distributed object store. Instead, we can just respond directly to the object's owner with the value of the object, and the owner then copies this value into its local in-process store. From there, getting the value of a small object is also pretty straightforward. In the code, we did this by calling ray.get on the object ref returned by the mean task. This is implemented with a lookup to the local in-process store. Then we just copy the value to Python. We can do something similar to handle small objects that get passed as a task argument. So for example, let's say that we actually decided to pass the final object ref to another task foo. Once the value is ready, the driver will copy the value from its in-process store into the task description, and from there, the worker can access the value directly. Okay, so now that we've created all of these objects, how do we actually get rid of them? That makes it easy to free small objects quickly. So once the driver sees that the resulting object ref has gone out of scope, it just erases the entry from its local metadata. We can do the same thing to erase the array object ref, but this time, since the actual value was stored in the distributed object store, we also have to free that memory. There are two kinds of object copies that can exist in the distributed object store. I mentioned earlier that one of these is known as the primary copy, and Ray will pin this copy to make sure that at least one copy of the object is always available. So that means that we also need to figure out when we can unpin this copy. During the object's lifetime, we can also create multiple secondary copies. For example, this one got created because we executed a task there that needed the object. Secondary copies might get freed before the object has gone out of scope. For example, if node 3's object store reaches capacity, we might free it early. Ray will eventually and automatically free both primary and secondary copies. And to do this, the node that has the primary copy will ask the object's owner when the copy can be released. In this case, the reference has already gone out of scope, so the owner responds saying that it's okay to release the array. The primary node frees the array once it receives the reply, then broadcasts this to other nodes to free the secondary copies. This way, we eventually end up back in the original state and ready to execute more tasks. So you might be wondering, what do I actually do if I have a memory issue in my program? Well, next I'll go through a brief demo of some of the memory debugging tools that Ray provides. I'll show you how to take an out-of-memory error in your application and debug it using the Ray memory dashboard. This is a new feature that was contributed by Max Fitton, and I definitely encourage you to try it out and send us any feedback. So here, I've actually just taken the same example that I've been using in my presentation, and I copy-pasted it into this Python script. So here we have the random task, which generates a 100 megabyte array of random integers from 0 to 10. And we have a mean task, which takes in an array and returns the mean. So let's start by starting up a standalone Ray system. And we can do that just by calling ray.get. So you can think of that as starting a one-node cluster on my laptop. Since we're going to be trying to trigger an out-of-memory error, I'm going to make that a bit easier for ourselves just by setting the object store memory to 1 gigabyte. And so that means that we can store about 10 arrays at a time. So next, we'll start computing some means in parallel. So first, I'll generate some random arrays. And this will generate about 20 of them in parallel. And then I'll pass each of those arrays to the mean task. And then finally, we'll block and get the results using ray.get. Okay, so now let's see what happens when we run this. So we can see that almost immediately we're getting these out-of-memory errors. And so for some context, the way that Ray reports out-of-memory errors is by looking at the local object store capacity when a worker tries to store an object in its object store. So here, when a worker tries to store the array in its local object store, if it sees that it's out of memory, it'll wait for some time so that objects can get freed, and then it'll try to put the same object into the object store again. And the default setting is to do this up until about 30 seconds. And after that, if the object store is still full, then the worker will return an exception to the caller saying that it was out of memory. So in this case, that's what happened. At this ray.get call, we actually got an out of memory exception because at least one of the workers couldn't store its object into the local object store. So now let's try running this with the Ray memory dashboard to see if we can get some more information. So to do that, I'm actually going to do a little bit of a hack here just to keep the driver alive because we don't want it to error out on the out of memory exception. And this time I'm going to run this again. Okay, so now let's try running that, and this time we're going to visit the dashboard. So we can look at this dashboard URL. And some of this might look familiar to you. So initially we'll see this resource level usage where we can see things like CPU. We're going to go over to this memory usage, which tells us information about all of the references that are currently held by workers in the cluster. So each worker will report information about the objects that it has a reference to, such as a unique string and the object size. And in this case, an object size of question mark means that it hasn't been computed yet, and also a reference type. So for example, used by pending task means that it's an argument to a task that hasn't run yet. Another cool thing is that we can actually group the object references by stack trace. And so the stack trace here refers to the stack trace where that reference was initially created. And we can see that there are actually two different groups of references here. One of them that was created at line 20 of our program, and another that was created at line 21. And both of them have 20 objects each. So if we go over to our code, we can see that at line 20, these were the array objects, and at line 21, these were the mean objects. And that makes sense because if we look at the array objects, the total memory that was used by these objects is really large. We have almost 1 gigabyte of memory used by the array objects. So in the examples that I showed you earlier, each array object was supposed to get freed as soon as the downstream mean task finished. But for some reason, they're not getting freed in this case, even though some of the mean tasks are finishing. And we know that some of the mean tasks have finished because if we look at the object size, some of them have actually already been filled in, so there's no longer a question mark. So that means we're still keeping around all of the array objects, even though some of the mean results are actually available. And we can look at the dashboard to give us a hint here, because if we notice this line, it says that we have 17 of these local references. And a local reference is a Python object ref. And if we look at the code now, we can actually see that indeed we're storing all of the array references in this temporary list, and we're never deleting that list from Python. Okay, so we can actually fix this pretty easily just by not storing these temporary variables. So instead, I'm going to create a list of means and just create the tasks in a for loop instead. So I'll create this temporary variable A, and then I'll pass this into the mean task. So now if we run this again, this time we'll visit the new dashboard. And this time when we look at the memory tab, we should be able to see that most of the references have actually gone away. And so here, this is looking a lot better because we only have 21 objects left in reference instead of more than 40 before. And if we look at this groups by stack trace again, we can see that there's only one of these array objects left. And that makes sense because we actually have this one left over from the for loop. Okay, cool. So now if we actually run this completely, I can get rid of this time.sleep call. And maybe let's say we want to print out the mean of the means. And since these are all numbers from 0 to 10, this should print out a mean of around 5 for all of the arrays. Great, so it looks like that's working. Okay, so hopefully that gave you a sense of how memory management works in Ray. But if you're a Ray user, actually the ideal case for me is that you never have to care about this stuff again. And that's because as system builders, we're always trying to make sure that Ray takes care of all of the hard stuff. And that way you can just focus on writing your application. If you are curious to learn more, you can check out our recent white paper and also find us on GitHub. Thanks, and I'd love to take any questions.